All right, welcome to the grand finale of this Explainer series. Today we're taking a pretty fascinating descent. We're traveling all the way from the abstract digital ether right down to the bare metal. In this 12th and final installment, we're zeroing in on that exact magical moment where on-chain digital state reaches out and triggers actual physical execution right here in the real world. So you might be wondering, how does abstract, completely untrusted code floating out there in the cloud actually move a motor on your desk safely? This is essentially the ultimate question of the agentic web. As AI agents increasingly generate and execute code automatically without any human review, answering this means we have to safely connect highly abstract backend execution with tangible hardware. We literally have to map a perfectly secure digital intent to a physical outcome. To organize all of this, here is our roadmap for the journey today. 1. The cyber-physical divide. 2. Sandboxing the AI brain. 3. Anchoring state with ERC 7827. 4. Crossing the semiotic bridge. And finally, 5. Physical execution via Cheerbot. It's a direct, step-by-step descent from the cloud sandbox all the way down to a physical leaf node. Okay, section 1, the cyber-physical divide. Let's just get right into the absolute chaos of trying to map digital ledgers to physical machines. Historically, trying to bridge the digital and physical world has been, well, a total mess. Traditional event-driven programming is a lot like falling dominoes. A single delayed signal, an event firing twice, or a slightly out-of-sync hardware state, and the entire sequence is ruined. To cross this divide reliably, our new architecture demands strict, bit-perfect, deterministic execution, absolutely no exceptions. What's really interesting is the ideological clash at the foundation of this architecture. The source materials actually ban the classic upside-down tree data metaphor. They literally classify it as apostasy. And why is that? Because untrusted code simply cannot float around in the digital ether. If you want to control physical reality without causing catastrophic failures, you absolutely must be perfectly anchored to a definitive root. Which brings us to section 2, sandboxing the AI brain. Because before we can anchor anything, we have to start in the void of the cloud, where untrusted code and AI agents must be perfectly isolated. So, WebAssembly and WASI, they create this incredibly secure, memory-safe boundary for these agents. WASM relies on linear memory isolation, structured control flow, and explicit capability-based access to system resources. It's a massive upgrade from traditional containers, for sure. But, as the source literature points out, while it does a great job restricting unauthorized memory access, it still faces real risks of resource exhaustion from malicious code that might try to monopolize your CPU cycles or I/O bandwidth. Now, if we want to build a truly hard boundary for these agentic brains in a jar, we have to contrast two leading approaches. On one side, process-shared V8 isolates. On the other, hardware-enforced micro-VMs. V8 isolates are what power platforms like Cloudflare Workers, separating scripts within a single process. Micro-VMs, though, provide a dedicated guest kernel and a much stricter hardware boundary. When you put them side by side, the differences are pretty stark. V8 isolates are insanely fast. They boot in under a millisecond. But they lack the ultimate security of full hardware isolation. Micro-VMs, using tech like Firecracker or Hyperlight, give you a true hardware boundary in just 3 to 8 milliseconds. By restoring from a snapshot instead of doing a full cold boot, Hyperlight acts almost like an embedded library for your agent stack. It gives you VM-grade isolation at absolutely blistering speeds. The big takeaway here? A sandboxed AI model is basically just a brain in a jar expressing intent. It's just text in, text out. It desperately needs a harness, a secure execution environment, to actually fetch URLs, run shells, and call tools safely, without risking the entire host system. Moving right along to Section 3, anchoring state with ERC 7827. Once our secure sandbox generates a verified intent, we travel down to our digital root to anchor it securely on the blockchain. To anchor this state flawlessly, the architecture relies on a LIFO, or last-in, first-out, structure. Think of this single-entry bookkeeping like an ancient, tamper-proof clay seal used for ledgers back in antiquity. We're essentially recreating that perfect seal digitally, which completely rewires how we verify data on-chain. And this is where Draft ERC 7827 enters the picture. It's an incredibly rigorous standard that acts as a bit-perfect, mathematical smart contract layer. It manages structured JSON directly inside smart contracts. It brings high data availability right to the client side, allowing developers to pull the latest state with the JSON method or check the chronological history with the version method. Basically, it makes Ethereum RPC calls as easy and familiar as standard REST calls. Because of this LIFO setup, you really only ever need to query index 0 to get immediate, definitive proof of state. If a smart contract needs to know the absolute latest command, it just glances at the top of the stack. You skip parsing massive, expensive transaction histories entirely, and you achieve total determinism instantly. All right, section 4. Crossing the semiotic bridge. Now we're traveling further down the trunk, translating mathematical consensus into physical action via what the sources call the semiotic bridge. This structured bridge follows 4 very strict phases to keep causality totally intact. First, anchoring the state via ERC 7827. Second, wrapping it legally via a Kali smart contract, which establishes a liability-limiting legal entity. Third, applying human cryptographic signatures via the kernel sign protocol to verify human configuration and, quote, sweat. And finally, hitting the hardware via physical actuation. To actually fund and route all this seamlessly, we rely on a multi-chain topology. We use the X402 protocol on Polygon for machine-to-machine micropayments. It actually updates the old HTTP 402 payment required standard, which lets AI agents evaluate costs and pay for resources totally autonomously. Meanwhile, we use Flow's blockchain as the highly secure immutable registry for the master JSON state and our administrative pseudo commands. Finally, Section 5, Physical Execution via Cheerbot. We have reached the absolute bottom of the funnel. This is the leaf node where pure math becomes tangible movement. Say hello to the Cheerbot. It's this cheerful 3D printed desktop robot that just patiently sits there reading the on-chain LIFO tree. Tucked right inside this little shell is a localized $15 Raspberry Pi acting as a micro-host. It reads the JSON state contract, just waiting for a verified state change, kind of like a tip from a live stream audience member. So when that tip or command hits index 0, the internal Node.js engine parses it, and then the magic happens. The Raspberry Pi fires raw electrical signals straight through its metal GPIO pins. These tiny metal prongs literally translate code into physical reality. They move a motor, turn on a light, or tick an ENS name across a screen right there in the real world. The source docs actually dropped this fantastic quote. AI agents are really just deterministic scripters. The human pilot applies the intent, but the agentic cell executes the sweat. It perfectly distills this whole journey we just took. The micro-VM sandbox safely scripts the intent, the ERC 7827 blockchain contract anchors it, and the Fizzle leaf, the Cheerbot, executes the sweat. We've gone all the way from the isolated cloud-based brains of WebAssembly and micro-VMs across the digital ledger straight into hardware that literally spins a motor on your desk. As we wrap up this explainer, I'll leave you to ponder this. As our AI structures achieve this bit-perfect real-world actuation, what are the actual limits of cyber-physical commerce? When machines can think securely, pay autonomously, and act physically, what exactly comes next?